All right. Thank you for the introduction. My name is Moritz Kontak, and I'm presenting our joint work with the Ruhr University Bochum, the University of California, San Diego, and the independent researcher Felix Domke. All right, to start off, I guess most of you guys have seen the coverage in the media regarding Dieselgate in the last 2 years. And our motivation here was to actually look at defeat devices and their implementation from a system security point of view. But before we go into the details on how the defeat devices are implemented, let's recap a bit. So the Dieselgate scandal was more or less set off by a study performed by the International Council on Clean Transportation in May 2014, where they tested a few Volkswagen cars and actually found out that on the real road, the cars emitted up to 40 times the allowed amount of nitrogen oxides, but this behavior didn't show during testing, so they were clean driving when they were tested. So there was some communication between Volkswagen and the regulators, and actually this caused the EPA to issue a public notice of violation of the Clean Air Act to Volkswagen. This in turn set off several lawsuits in which Volkswagen had to pay money spend money on buybacks on emission projects and actually pay fines as well. So this led to Volkswagen announcing in November 2016 to actually stop selling diesel engines in the US altogether. Also, the beginning of this year, Volkswagen actually admitted to the use of defeat devices in the period of May 2006 to November 2015. All right. Okay, to get an idea of how a defeat device works, we first have to get some knowledge on modern diesel engines. So what you see here on the left is the engine itself emitting some pollutants, namely soot, also called particulate matter, nitric oxide and nitrogen dioxide. And on the right, you have the tailpipe where the exhaust gas goes out. And in between, you get various exhaust gas after-treatment systems. So the first one being the diesel oxidation catalyst, which basically oxidates nitric oxide to nitrogen dioxide, which is a preferable reagent in further components. Then we got two filter systems. So basically, we got the diesel particulate filter, which binds soot on its surface, and we got the NOx storage catalyst, which in turn binds nitrogen dioxide on its surface. So they only got a finite amount of pollutants they can actually trap, so they need to be regenerated regularly. So this is done by raising the air temperature in the engine and just blowing hot gas through both filters to actually burn off the pollutants on the surface of the filters. Okay, we also got an additional system which is called exhaust gas recirculation, also abbreviated as EGR, which replaces some amount of the engine's air intake with exhaust gas. This leads to some of the nitrogen oxide or nitric oxides being burnt in the combustion chamber already, which reduces the amount of nitrogen dioxide in the exhaust gas. So finally, if you got a bit more money in your hand, you can replace the NSC by a SCR, which doesn't need to be regenerated because it reduces the amount of nitrogen dioxide in a chemical manner. However, this requires the engine to have an additional urea fluid tank, which is used in this chemical process, and this urea tank needs to be refilled regularly as well. All right, and all these components are actually controlled by what is called the engine control unit. So it takes sensor readings from different parts in the exhaust gas pipeline and issues regeneration and controls engine behavior in a way that pollutants are minimized. All right, so we got these complex systems, and these obviously lead to trade-offs. So we want to reduce the amount of nitrogen oxides, we have to do so, and this can be achieved by a high EGR or SCR rate. However, there are also limits on soot emissions. So we cannot have too much soot in our exhaust gas. This is also regulated, and this is also the first problem. As you see here, if we get a higher EGR rate, we reduce the amount of NOx in the exhaust gas, but we also increase the amount of soot. So this is the basic trade-off we're facing here. Also, if we have high soot emissions, this causes wear on the GPF filter. So we have to regenerate it many times, and this is in conflict with the durability standard of the filter. So this basically binds filter lifetime to an amount of miles where the filter has to hold up, and this might not be the case if you regenerate it regularly. Similarly, if you have a high SCR rate, this is in conflict with the service interval, which binds the refill of the urea tank to a specific amount of miles. All right, now we know about the trade-offs, but the question now is how are those tested? Basically, you put the car on what is called the chassis dynamometer. So the car is fixed on it, so you can really steer, but you can still accelerate, decelerate, and so the tires are on a rolling road, basically. Then you collect the exhaust gas and analyze it later. This begs the question, how do you drive? So which driving is representative? And luckily, this is standardized. In the picture, you see the federal test procedure is used by the EPA to perform emissions testing. And as you can see, this directly specifies the way you drive. So you got time on the x-axis and vehicle speed on the y-axis, and you directly follow this profile. Of course, there are different tests for different jurisdictions. So for the EPA, for the CARB, for the European Union. But the important part is that they are standardized and publicly available, even to the car manufacturer. All right. So if we drive the cycles and collect the exhaust gas during the emissions test, we now have to take care which limits are there in place from a regulatory point of view. So on the x-axis here, you see the nitrogen oxide limits, and on the y-axis, the particulate matter or soot limits. So we look at the European norms and also the one here in effect in California. So those are decades old, and you see that these get increasingly strict over the years. Currently, we're mostly concerned with the bottom left corner of this image. Now imagine you're a German car manufacturer who built a shiny brand new engine for which conforms to the EU 5 norm. But you are now facing introduction of the EU 6 norm. Now you have to lose nitrogen oxides by roughly half, the half, so you have to lose half of your nitrogen oxides. You face a similar situation if you get the car compliant to EU 5 norm, and now you might want to expand your market to the Californian area, where you're subject to the low emission vehicle norm, and you still have to get rid of even more nitrogen oxides. So this might be a hardware problem. So if you do not have the time or the funds to redesign your engine, it is very tempting to the car manufacturer to actually solve this in a software level, because you know the way the car drives when it's tested, and you can actually react to it, and this is very tempting. This led us to the analysis of the Volkswagen AG defeat device. Basically, what you see here on the left is an excerpt of the documentation. And you also already see various reoccurring patterns. So this is what they call the acoustic function, and they encode profile checks. So you got curve queries at a specific point X, and you always get two curves, a bottom curve and an upper curve. And what you're doing is basically an interval check using another engine parameter. So if it's within those curves, the profile matches. And if you look at where the engine parameters come from, you see that X is the time since engine start and Y is the distance covered so far. Already sounds a bit familiar? Okay, so we can actually plot them. Seconds on the X scale, kilometers on the Y scale. The bottom curve and upper curve. Now what happens is that if the car's driving behavior happens to be inside the white area, the subsystems are tuned in a way that the car drives cleanly. If there's no profile that's matching at all, so no white area in any profile, the car drives not cleanly anymore. So if we now plot known emission test cycle, for example, the federal test procedure we've seen earlier, into this figure, this happens. So if the car's driving behavior is inside the white area, we drive cleanly, and this specifically follows the federal test procedure. So this is an exact test on the way the car is tested on the chassis dynamometer to ensure that during testing the car drives cleanly. We can look at other profiles, for example this one, And this happens to coincide with the European test cycles that are used to test emissions in cars. Further, there's a rather accepting profile, which is actually pretty good because we can match a whole bunch of emission tests at once. However, there's a problem. So imagine you're driving your kid to the kindergarten, and there's a high chance you might accidentally follow this profile, which actually is bad because clean driving isn't made for a longer time because this violates the durability standard. So what they did, they expanded this check to do this. All right, so at least I hope if you drive your kid to the kindergarten, you move the steering wheel, but you can't do so on the chassis dyno. So this effectively allows them to have an accepting profile with a specific check to target chassis dynamometer tests. All right, now we're interested in how this function came to be and looked at some documentation. And we see that in red, we got the number of profiles, and in blue, we got the number of subsystems affected. And we see that only starting May 2007, they started using profile checks, and also the amount of affected subsystems increased. And this also includes more and more emission-related subsystems. So yeah, maybe they used, so there's the question if the function originally had a benign purpose. It was then later retrofitted with the defeat device logic. Now we wanted to know which cars or which firmware images actually check against those cycles. So we built CurveDiff. It's based on PyPy and IDO Pro, and actually analyzes electronic diesel control EDC17 by Bosch, which uses an Infinity tri-core processor. And yeah, we basically lived it to SSA form and to be able to use common analysis techniques. And on the right, you see the output. So we just plug in a firmware image, let the tool run, and get a nice listing of the emission test cycle it specifically tests against. This is done in 2 to 3 minutes. So we were able to run it on over 900 firmware images spanning 8 years, so 2009 to 2016, and found out that more than 300 of them tried to detect at least one emission test cycle. All right, so this begs the question if there are other vendors which also employed similar devices. So we got both firmware and documentation for Fiat 500X. And what you see here is basically the logic which issues NSC regeneration. If we recap from earlier, we see that more regenerations actually lead to cleaner driving because the more pollutants can be trapped in the NSC. You might already see 2 parallel logics here, which are labeled conveniently. So we got DNOx during homologation and DNOx during real driving. Real driving, I know of, but me being not a native speaker, I had to look up homologation actually, so I went to Google, and other people also asked themselves, what is this? And this happens to be the process of certifying vehicles or a particular component in a vehicle that satisfies the requirements set by various statutory regulatory bodies. This sounds kind of fishy, right? So we got parallel logics. Starting on engine startup, both logics are in effect. So we got the homologation logic on top, which issues compliant NSC regeneration. Also, we got the real driving mode on the bottom, which seldomly regenerates the NSC. During startup, it's not much of a problem because both are active and issue regularly regeneration. However, we found that after 1,600 seconds, only the lower subsystem, the lower path is in effect, which issues seldom regeneration, which makes the car drive not cleanly anymore. And those 1,600 seconds happen to coincide with the test of with the duration of standard emission tests. So this is quite an easy way to drive cleanly during the testing phase and drive in a more polluting mode afterwards. Okay, coming to some implications. We've seen the general state of emissions testing. So we got strict regulations, public test cycles, and what is basically done is black box testing on the hardware. So this allows manufacturers to actually check the driving profile or insert a time, as we've seen here. There has been an effort to introduce what is called portable emissions measurement, in which you just have a system you strap on the car and you can drive around freely in the city and then collect and analyze the exhaust gas. This is a nice idea and it might work in practice, but we argue that this doesn't solve the underlying problem, because compliance testing now is a software verification problem. We got software running on the engine, and this actually triggers the regenerations and such. And it's so easy to hide in software, and black box testing is insufficient in the general way, because you might not be able to trigger all the conditions that happen to switch between both modes. And portable emissions measurements only sidestep the problem. We cannot fingerprint the driving profiles anymore, but we can still have timers, or maybe we can have environmental checks. Further point is that software analysis facilitates large-scale testing. So we do not need to obtain a car, put it on a chassis dyno, drive it for 20 minutes, and then analyze the exhaust gas. What we can do now, or what we can work for, is that we just take a firmware image, put it into a verification system, and 2 minutes after get out some results on whether the car is in compliance or not. Okay, coming to the conclusion, we analyzed 2 modern defeat devices in software, one from Volkswagen AG, which is using driving profile checks to basically fingerprint the situation where emissions test is going on. And we got the Fiat 500X, which is doing a similar thing by using a specific timer. Then we also performed a large-scale study on the Volkswagen AG defeat device. We tested over 900 images and found out that around 300 of them tried to detect at least one test cycle. In general, we conclude that black box testing, black box emissions testing in general is insufficient, because it's easy to cheat using software, and there's a high incentive to do so. So further regulations put stress on the car manufacturer, and because they know the exact procedure that's used to test the cars, that's a high incentive to find a software solution to a hardware problem. And in general, we notice that software verification of compliance poses a new challenge to the whole emissions testing scenario. With that, I would like to conclude, and I'm happy to take your questions.
All right, let's thank the speaker, please. Some people are approaching the podium, and then they move away. Paul.
Paul Vinorcha. Non-technical question. Any speculation as to how they were able to keep this secret for so long? Because we know one of our principles is secrets leak, and it seems they kept this quiet for a long time.
So you mean how this managed to not crop up earlier?
Yeah, like you would have thought there'd be some leakage of that information.
I think the main problem here is that it didn't show up in the actual emissions testing, because this is hard to do on a large scale. You can just pick some cars, put it on the chassis dyno, try to test them, but you cannot really get the whole number of cars from, say, Volkswagen or so, and check against those, and also not check against various other conditions. So imagine you got a defeat device which implements temperature window to basically fingerprint the exact temperature in the test lab. So you would have to take the car, put it into a cooling chamber, so to say, to try to trick the defeat device. And basically this is hard to do on a large scale.
Federico.
It's not a very serious question. It's just like an anecdote, so you can maybe reuse it in other talks. I'm one of the owners of a Volkswagen vehicle who was recalled back by the factory to upgrade the firmware. I brought the vehicle, they upgraded the firmware, and they gave me a battery pack as a gift. And after a month, they recalled that because it was defected.
All right.
Very nice.
Thanks.
Robert.
Rob Cunningham from MIT Lincoln Lab. I'm wondering, are we going to be heading in a direction where the people who do the certification have to do some sort of digital signing of the thing that they actually tested, and then we now have to start worrying about how we load the cars up with the next revision to their firmware? Do you think we're headed in that direction, or is there something else that could be done?
So in general, this is a question of transparency between both the car manufacturer and the regulators. So currently they can only do black box testing, and they may get a firmware image, but I don't think there's infrastructure into place to be able to analyze them in depth. So this is an issue that should be addressed in a way that the car manufacturer actually goes toward the regulators and exposes some of the engine internals for them to be able to verify that the engine is actually in compliance.
We have to stop here, sorry. We have to leave time for other papers. Thank you very much.